Good afternoon, ladies and gentlemen. Welcome back. This is Mr. Chen, teaching part 3 of our lesson for MPM1D, grade 9 math, academic, and enriched. Linear investigations. Today, we're going to be looking at direct versus partial variation, lines of best fit, the concept of extrapolation and interpolation, and investigating in DT graphs. As always, please feel free to refer to your textbook and or the CEMC resources that are at your disposal. This is kind of just a summary, just to make sure everyone's okay. So we can just move on forward to our next unit. At any time, please feel free to pause the video in case you find I'm going too fast. And I'm just highlighting the main ideas. So for the first concept, what we're going to look at is this idea called direct versus partial variation. And what is direct versus partial variation? Well, first of all, let's review. Direct variation and partial variation. I'm going to first write it as an equation, a generic equation. Direct variation looks like y equals mx, whereas partial variation will look like y equals mx plus b. A lot of you already know what we're talking about because it's pretty straightforward. Visually, let's just draw a quick sketch. Direct variation. Oops, see, let's try that again. How come it's not going the way I want to? Let's erase that. Let's move it. That is not direct variation. There you go. That's direct variation. Notice it goes to the origin. That's partial variation. Oops, still not on drawing. Oops, too thick. What's going on with me, Mr. Chen? This is my third take of doing this. Much better. Partial variation. The line intercept looks like that. There you have it. Something goes to the origin. I cannot spell today. Zero comma zero. Does not go to the origin for the partial variation. Also notice from a table of values, if we had a table of values, and here's another example, not this quite example, but let's just say, notice the initial value, starting point, or whatever, the y value will be 0. And then maybe that could be 2, maybe 4, maybe 6. So the key thing is that the table of values would show you a 0, 0. Whereas partial variation, if we had it, would be something like this, maybe 0, 7, then 2, go down to 6, go to 5, go down to 4. The key thing here is that it does not go to the origin, and notice the initial value is not 0. So that's why we have this idea of the y-intercept. I just drew 2 rising lines, but it could definitely be falling lines. Okay, so that's what we have for that. We're now going to go with lines of best fit. It can also be a curve too. And so let's just draw some straight lines really quickly. I don't know why it's not stretching for me. Pretty good. And let's just put some points. Let's say we have a point here, data point there, 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 let's just say, data point way up here, data point there. So line of best fit, lines of best fit, we're trying to get a straight line that kind of goes through most of them. And this is very subjective. So there's no written rule. Eventually, you're going to learn in data management the calculation or the linear regression for that. But as it stands, lines of best fit, right now, we try to get points that are on both above and below it. Now, I am using a ruler, so you can't see it. But maybe you know what, maybe I won't. Maybe we'll just draw it. Line of best fit. And as you can see, I'm trying to get a pretty good balance. Notice that top point. Maybe get something like that. That could be our line of best fit. And we could definitely find the equation of the line. A lot of you also notice when I'm doing circling in green, this can be probably what's called an outlier. Not always do we have to take it into consideration, but sometimes in data collection, we just kind of ignore a point that doesn't really kind of go with that pattern. So we have to be careful when we're collecting that data. Just really, really quickly, the line of curves the best fit. Let's just erase this really quickly. Curve of best fit, it's very, very similar. And let's use some red dots. So maybe get something that looks like this. So I get something like that. Now this one's gonna be a little harder to draw, but a curve of best fit, all we have to do is maybe realize it's not gonna be a straight line. I mean, we could draw a straight line too, kind of, but if they're saying that the data is probably curve of best fit, we're trying to get to the point. Let's look like that. And this is clearly nonlinear. So definitely, if we were to find the second differences for this, the second differences probably could be the same, right? Let's clear all that. Moving on to the third topic. I think I wrote extrapolating. And interpolation. Really, really quickly, this means to extend beyond the data. This means to look within the data. So let's draw again 2 lines. Over here, let's just say, so X and Y. And again, let's just use some data points. Let's just say we have some data that's kind of like this. You kind of got a table of values. And so you're going to draw your line of best fit, right? Let's use red. So this is line of best fit. Well, this orange dot that I'm going to do is an extrapolation. Because we look beyond the data set, and we could read what its values on X and what its values Y is. That's extrapolating, looking beyond that data or extending it. Notice, we probably can even go further, thinking that this red line could keep on going straight, probably a descending line, probably a negative slope. But that's what we can infer. So that's why extrapolation is trying to see what's going on or patterning beyond. That's why, for example, we use it in forecasting, in sports, in finances, even in health, right? So we're looking for those data that are going beyond what we collect. Sometimes we just collect that data, but we don't know. And so sometimes we have to do what's called an interpolation. And interpolation means look within the data. So this green data I'm going to put in here, because we're assuming it's a straight line, maybe it's inside the data set. Notice that green dot is interpolating inside there. We can definitely read some values. Maybe we wanted to figure out a data set that we didn't have or got corrupted. So we're just trying to figure out what that interpolated data set is, right? So that means just looking within or beyond, right? So a lot of you already know how to do this, especially if we don't have that data set, right? So for example, maybe you missed an assignment in English class, and so the teacher would interpolate to see what mark you would have gotten if you're going by the steady pattern. Maybe you're improving very well, and they actually kind of look to that from your previous trends. So that's extrapolation, interpolation. Final concept is investigating distance time graphs. As a refresher really quickly, speed is equal to distance over time. And so one more time, let's just get this out of the way. We have a y-axis there, we have an x-axis there. This time, on the x-axis, this is maybe going to be time, let's say in seconds, and then distance here, meters. We did an example in class where we looked at the motion detector, and so some of you actually understood what we're doing. I'm just going to do one example just to showcase things, if that's all right. And let's just say we had a line, well, actually a couple of lines. Looks like this. Oopsie. Put that back. Try a new line here. It seems to be picking it, and I don't know why it went away. Let's try that again. So we got two lines there. And so this is a distance time graph. Notice it looks like two straight lines, right? And it is two straight lines, right? So to talk about this, we tend to kind of sometimes like just divide this into two parts of the story. So the first part of the story here, what could you talk about? You can talk about the distance. And in fact, the object isn't moving. How do I know that? Well, on the y-axis, that's our distance. And that line, it seems to be a horizontal line. The slope is also 0. And there's no rise, there's no run. There's no rise, it's only running, right? So this particular motion, whatever it is, it's just standing still, right? So when slope is 0, a lot of you actually understand that this looks like a rate of change. A lot of you actually understand that's the rate of slope. So that's the first part of the trip, or the first part of the object. The object isn't moving. So for horizontal lines, that's what a lot of you understand. Second part of the trip, well, it seems to be a falling line, but it's clearly a straight line, right? So the object is moving steadily. And the reason why it's steadily, it's a straight line. But also, what direction is it going from? So this is a time where we can be creative. Maybe at this part of the story, where we start at the beginning of this graph, maybe that's school, right? Maybe that's a school where we used to go. And maybe this is now coming back home, right? So at school, you'd stay at school for a while, and then the second part of the trip is maybe coming home at a steady pace because you just want to walk. You want to just be resting kind of constantly, right? Heading home. So we can interpret these distance time graphs by telling a story of the object, right? It could the object be maybe your bicycle or whatever. What device could be moving? Maybe it's riding a bicycle, right? Just coasting down on the street, with no speeding up, no slowing down. So that was a quick summary of all the 4 topics that we were covering, and this ends our linear unit. And hopefully, in the next couple of days, we'll actually start the measurement unit or the geometry unit. Okay. Hope you're doing well. Hope you're being safe. And once again, I thank you and trying to follow up or keep up with your studies. Have a nice day.